Alright, in this lesson we're going to start talking about probably one of my favorite concepts in physics, one of the most useful rules that exists in the universe, and that's the rule of conservation of energy. And it's one of the fundamental rules of the universe is that energy can neither be created nor destroyed. Put an asterisk by it here, and I'll get to that asterisk in just a second. In chemistry, when I taught chemistry, I would call this the first law of thermodynamics. And it's a basic principle found in many scientific fields. Basically that you can account for all the energy of a system by adding energy gains and losses. This idea gives us a very powerful tool to solve a wide range of problems with. Now, I put this asterisk in here because Einstein's famous equation E equals mc squared suggests that mass is also a form of energy. And in reality, well, it is. So this idea of energy cannot be created or destroyed can sometimes get a little bit complex, depending on what type of situation you're dealing with. I say, don't believe me, check out the atomic bomb or nuclear power and how that works. Check out fusion in the sun and how that works. You'll see that, sure enough, mass is being converted into energy in all of those situations. Now, the nice news is, in the context of this course, you're never going to need to worry about that. But I do think it's nice to have in the back of your head that when we talk about energy can neither be created nor destroyed, it's a little bit more complex than just our conservation of energy equation. Just that our conservation of energy equation is a model that works very well for lots of physical systems. So I have an equation that I call the energy balance. Basically, if energy is conserved, I should be able to take the energy before something happens, the energy after something happens, and add in any work that happens in between the before and after and get the same value. And in this case, I'm going to say all kinetic energies before plus all potential energies before plus any work done by non-conservative forces from before to after is equal to all kinetic energies after plus all potential energies after. So as you might imagine, sometimes these equations can get pretty long. There can be lots of different terms. There are multiple forms of kinetic energy, translational, rotational. There's multiple forms of potential energy, spring, gravitational, electrical. Multiple different forces can do work that are non-conservative forces. What you start to do is you start to begin to cancel out the terms that don't matter in the context of your problem. So let's try a problem like this. And we have a 5 kilogram block. It's going to slide down a 5 meter ramp. 5 meters down a ramp angle to 20 degrees to the horizontal. Coefficient of kinetic friction is 0.2. If the block started at a speed of 1 meter per second, what is the velocity of the block at the bottom of the ramp? Wow. So there's a lot of different things going on here. The block starts at the speed. It's obviously going to probably accelerate down the ramp. We can find the speed at the bottom of the ramp. So let's apply conservation of energy. One way we could conceivably do this is to use Newton's second law, and then kinematics is one way we can do this. The disadvantage to that way is if this wasn't a constant 20-degree slope, we could no longer use Newton's second law because, well, the acceleration would not be constant anymore. So let's use the energy balance. And so what this would mean is that 1/2 mv initial squared plus mg h initial minus fx, and what little f is the frictional force, equals 1/2 mv final squared plus mg h final. What I'm going to do is call h final 0, that we're at height of 0, and so I need to find h initial at some point because it's going to be whatever this height is here. The other thing I need to do is find out what f is, and maybe my m doesn't matter, I don't know. So let's find f first, and the way we would find f is to do mu k times normal force. And so let's see if we can figure out what the normal force is. Those would be two of my forces, Fg and the normal force. Well, if I kind of figure out what the normal force is, if I look at perpendicular to this ramp, forces should equal 0. So mg cosine of 20 has to be the normal force. And so let's plug that in for normal force. I've rearranged it to mgx cosine of 20. The next thing I want to do is figure out what the height is. Well, first thing I can do, there's an M in all terms so that 5 kilograms doesn't matter. That's nice. Next thing I want to do is find out what H0 is. Well, if I look at that, I draw, and I made a right triangle, so H0 is x times sine of 20. So let's plug that in. And it looks like the only thing I don't know in this problem is V final. Multiply everything by 2, square root everything, and it looks like I rearranged by pulling gx out of all those terms. And so there we go. And if I plug in my values, I get 4.01 meters per second is V final. So this is really saying is that this only depends upon V initial x. The angle of the ramp and the coefficient of friction are the things that you can do to change this problem. So let's get another example problem. I'm going to have a block with a mass of 0.5 kilograms. I'm going to drop it from a height of 0.75 meters above a spring that has a spring constant of 25 newton per meter. And we'll talk about this in a little bit more detail later on if we haven't already talked about springs and forces due to springs. As the block compresses the spring, 0.5 joules of energy is converted into thermal energy. This is really talking about a non-conservative force, that something about this spring condensing, 0.5 joules of energy is lost by this system. How far does the block compress the spring? So let's do the same problem. Start with the energy balance. And one thing to point out is both the initial kinetic energy and the final kinetic energy are 0. It starts at rest when you drop it. The moment it compressed the spring to the maximum, it's at rest. So really we're just interested in changes in potential energy. So some things that I'm interested in is M, 0.5 kilograms, H0, which is 0.75 meters, the height above the spring that this block was dropped. K is 25 newtons per meter, and the work done by non-conservative forces is 0.5 joules in the negative direction. So I'm going to explain here real quick what's going on, and we have mgh initial plus work due to non-conservative forces equals 1/2 kx squared. This is the potential energy due to a spring, and x is how far was the spring compressed. Notice before this happened, the spring was not compressed at all, plus 1/2 mgh final. Now you might say, why isn't h final 0? Well, if this thing is 0.75 meters above the spring when you drop it, it hits the spring, and the spring compresses some distance, well, h final has to be some distance related to x, right? And in fact, h final and negative x should be the same value. That if I'm calling h equal to 0, the height of the spring before it's compressed, then the block actually moves negative x during the time of the compression. One thing to point out about potential energy is that I can say h is 0 at any location I want it to be. In this case, this might make it easier to do. There might be other ways you could do this problem. So here we go. We get this equation, mgh initial minus work non-conservative plus 1/2 kx squared minus mgx, and we're trying to find x. So what I can do is solve this whole left-hand side of the equation. I've solved for the initial potential energy and the work due to non-conservative forces. So that means that 1/2 kx squared minus mgx has to equal to 3.175 joules. And really the only way to solve this problem that I can think of is probably the quadratic formula. So I moved that over to the other side, did some work to plug some things in, plugged the m and g in, plugged the 1/2 times k in, and to get 12.5 newtons per meter times x squared minus 4.9 newtons times x minus 3.175 joules. Now to get to a quadratic like this, I run through the 3 techniques I have to solve it, are the techniques I have: factor, not a factor, perfect square, not a perfect square. So I'm really stuck with quadratic formula or graphing fairly quickly. I decided to graph this function and found 2 zeros, that this could occur at x equal to negative 3.45 meters, but that doesn't really make sense in the context of the problem, or x equals to 0.737 meters, which does make sense in the context of the problem. So this means is that the spring got compressed 0.737 meters during the time of compression. So that's kind of a quick overview of conservation of energy and how energy works. What we'll look at in the next lesson is power.